Hello delegates, my name is Peter Hills. I have practiced as a geologist and geotechnical engineer mainly across Tasmania for almost 40 years. I spent time at Renison, Mount Lyell and Beaconsfield, and more recently across a number of sites while at Pittencherry. This talk presents a summary of the current knowledge of Tasmanian rock stress. Rock stress is a bit of a nebulous concept, and although we can certainly see the effect of stress as the pictures of failed stress measurements indicate, we can't see the stress itself, and we can't even measure it directly. Nonetheless, it is a phenomenon that impacts on all excavations in the Earth's crust, particularly underground. The first measurements in Tasmania were undertaken during excavation of the Powattina Power Station in 1960 using flat jacks. Subsequently, measurements have been undertaken at 15 sites using 8 different techniques with varying levels of success. The majority have used the CSIRO developed hollow inclusion cells, or HI cells, which provide a full 3D stress tensor from a single measurement. All Tasmanian data was analysed in a paper I completed in 2020. Measurement sites are largely confined to the Western Tasmanian terrain. Some show a strong influence from geological features, topography and topographical anomalies. However, a sufficiently consistent picture across several sites allows for establishment of a generalised Tasmanian stress regime. A look at some of the anomalies first. At Renison Mine, as the stereographic image shows, the orientation of the major principal stress, sigma 1, is strongly aligned to the strike of the Federal Bassett Fault. As we will see, this orientation is distinctly different from that usually observed. At Hellier Mine, the orientation of sigma 1 is strongly aligned to the nearby Southwell River Gorge in the shallower measurements. The Fisher Power Tunnel, there was a significant stress impact when the mole-driven tunnel was driven under the edge of the Western Tiers escarpment, with significant spalling occurring in the circular tunnel in Permian sediments. And at Powattina, the vertical stress reflects a greater depth of cover, more like that expected from the retreating escarpment a few kilometres to the southwest. In effect, we are seeing a relic stress from a past era before that retreat occurred. Stress measurement and modelling led to the trapezoidal design for the roof of the Powattina Power Station in near horizontal Permian sediments. Stress relief slots in the form of closely spaced diamond drill holes were also used to draw the stress concentration away from the corners of the excavation profile. The effects that mitigated can be seen in the access tunnel, which was not so engineered. Stress modelling was also crucial to determining the length of steel lining required in the John Butters power tunnel to ensure that the static water pressure did not overcome the ability of the rock mass to contain it beneath shallow cover. Analysis of the 3D state of stress in Tasmania is based on the HI cell, as it is a recognised standard measurement technique and is the method of testing at most sites. The instrument is grouted into a pilot hole and an array of 12 strain gauges are monitored while the instrument is overcored, relieving the stresses. A biaxial test is undertaken on the recovered core to determine Young's modulus and Poisson's ratio, and the stress tensor is then resolved. 3 tests per site is considered desirable, and the table illustrates the determination of excellent, good, fair or poor site measurements. An HI cell is illustrated and a strain gauge array is seen on the side of the cell. The graphs show the output from the overcore and the biaxial test, with the output from each gauge reflecting its orientation on the cell, and in the case of the overcore, the orientation of the cell itself. It doesn't matter what the orientation is, as long as it is known. I should say that the graphs shown here are not always this good. This slide shows all Tasmania's 3D data. It is provided for your reference and perusal offline, and I don't propose to discuss it. All the results are shown, regardless of the quality of the measurement itself or the method. The key information for the user is the magnitude of the principal stresses with respect to depth and the orientation of those principal stresses. This slide illustrates the former. The graph on the left is the depth gradient. The average is based on the excellent, good and fair HI cell results at depths greater than 400 metres. However, all data is shown, and they give us the relationships of sigma 1 being 0.039 depth plus 10.7 MPa, sigma 2 being 0.035 times depth, and sigma 3 being 0.023 times depth. The graph on the right shows the stresses plotted against the first stress invariant for that particular measurement, that being the sum of all three principal stresses. It allows us to highlight measurements that might be anomalous for some reason. That from 1085 metres at Beaconsfield Mine is a clear example. It's not a wrong measurement, but it just doesn't fit the average pattern. Orientation is illustrated in the three slides. In the first, the excellent, good and fair results are plotted, and this determines the average Tasmanian condition. And we can see we have sigma 1 trending at 23 degrees to 261, sigma 2 trending at 15 degrees to 164, and sigma 3 trending 62 degrees to 043. The second slide illustrates a number of data combinations to identify anomalous results. This clearly shows that the stress orientation at Renison Mine is influenced by local factors, and we have already seen that this is the Federal Bassett Fault. All the others together combine to give the average stress tensor. This is somewhat different than the results obtained in Victoria, where the majority of measurements are in rocks of the Lachlan Fold Belt, which is equivalent to the Eastern Tasmanian terrain. The full data set is somewhat scattered, but the scatter can largely be explained by local features. We understand those to be geological or topographical features, and as we've seen in the examples to date, we can explain most of those. This slide demonstrates the determination of an indicative friction angle and upper and lower bound rock mass strength using the stress data. The details are somewhat beyond the scope of this presentation. I refer you to the references. In summary, the data is sufficient to determine a robust stress condition for the Western Tasmanian terrain, which is distinct from that defined in the Lachlan Fold Belt in Victoria. That is sigma 1, 0.039 times depth plus 10.7 MPa directed at 23 degrees to 261, sigma 2, 0.035 times depth MPa directed at 15 degrees to 164, sigma 3, 0.023 times depth MPa directed at 62 degrees to 043. And we can see in the table how this varies from that measured in the Lachlan Fold Belt in Victoria, and also how the ratio of the magnitude of the principal stresses is significantly different. The final slide is just the references quoted in the presentation that we've just been through. There are many more references relevant to Tasmanian stress in my 2020 paper. Thank you.